Today we're going to learn how to put the information about polynomials onto a graph. We're going to learn about turning points, also called a relative max or a relative min. It's the hills and valleys of the graph, and they occur between the zeros of the function. Another possibility is if a function has multiplicity. This is when there's a repeated zero, or the turning point is a zero of the function, or the maximum or minimum occurs on the x-axis of the graph. As I mentioned, today we're going to be looking at how to graph polynomials. When graphing a polynomial function, you first want to determine the end behavior. Now in this case, for end behavior, I just want you to sketch a little graph instead of writing it out in words so that you can match your sketch with your final graph to see if they're the same. In this case, notice that it is not in standard form. You have to find the term with the highest power to determine what the end behavior will be. We have an odd power, so it will look like a snake, and the coefficient is negative, which means it will fall to the right. Next, we'll find our zeros. So we set the function equal to 0 and solve for x. In this case, we can factor out an x squared and set each piece equal to 0. So x squared equals 0 and 5 minus x equals 0. Notice for the x squared we have a repeated 0. We have multiplicity of 2. The power on the x is 2. We could also write it as x times x and get two different answers for x equals 0. So note the multiplicity. This will be a turning point. Our other solution, adding x to both sides, we get 5 equals x, and we're going to write these zeros as ordered pairs as well. Finally, we will use a t-chart to determine the turning points. They will occur somewhere between the zeros. The graph will have to turn as I'm going from 1, 0 to cross the x-axis again. In our case, we do know we have one turning point at 0, 0, but we will have to have another turning point between 0 and 5, as the graph will have to turn to get back to the x-axis. So we will sub in those values between 0 and 5 into our function to determine where either the highest or the lowest point is, depending on if the graph is increasing or decreasing between the zeros. Subbing in 1, we have 5 minus 1 is 4. Subbing in 2, we have 20 minus 8, which is 12. Subbing in 3, we have 45 minus 27, which is 18. And subbing in 4, we have 80 minus 64, which is 16. Notice we found a turning point at 318. The graph will rise from 0, 0 up to 318, and then it turns to go back down to 5, 0. In order to fit this on my graph, I'm going to scale each of these by 4. And in order to make my x-axis a little bit easier to graph, I'm going to scale each of these by 2. Plotting my zeros at 0, 0 and 5, 0. Plotting my turning point at 318. You can plot as many of those other points as you choose to make your graph more accurate. Those are the minimum that you need to graph in order to show me an accurate sketch. Remembering what our end behavior looks like, it is falling from the left, turning at 0, 0 because of that multiplicity. We found another turning point at 318 and falling through the 0 of 5, 0. Taking a look at another example, step 1, sketch what this function will look like on the graph using end behavior. This time it is in standard form, so we'll look at the first term. The highest power is 4. The leading coefficient is positive, so it will open up. We might have a few turning points in the middle. Step 2, find those zeros, set the function equal to 0. And solve for x. In this case, we will factor by grouping. My first two terms have a common factor of x cubed. My second two terms have a common factor of 1. Factoring out that 3x minus 4, I am left with x cubed plus 1. X cubed plus 1 is a sum of cubes, and it does continue to factor. However, for our purposes of solving for the zeros, it's actually going to be easier to solve it in the format it's in. So I'm going to set each piece equal to 0, zero product property. Our first 0 occurs when I add 4 and divide by 3. If it's easier for you to graph as a mixed number, this is 1 1/3. Our other 0 occurs when I subtract 1 from both sides and take the cube root, which gives us -1. Third, we will try and find our turning points that will occur between the zeros. Between -1 and 1, the integer is 0. You do not have to sub in any fractions. Subbing in 0, we get a y value of -4, so we will use that for our turning point. Due to the scaling on this one, I'm going to call each of these 1. So my 0, -4 will be down here. -1, 0, and 1 1/3, 0. In this case, our graph will look like a parabola. We don't have more than one turning point between our zeros.